So this is the outline for today. So if we have more time, then we're going to talk about, this is pretty much chapter 1, if I remember correctly. But if we have enough time, maybe we're going to start on chapter 2, if not next class. So this will introduce you to semiconductors. What are semiconductors means? What are N-type and P-type semiconductors? Remember that there are two types of semiconductors, N and P-type. And if we put it together, that will form what is known as a p-n junction. This is the heart of the entire electronics, the p-n junction. It's the heart of diodes, it's the heart of transistors. That means entire electronics will be relying on what is known as a p-n junction, where p-type semiconductor, n-type semiconductor were placed together will forms a junction, so which is basically a p-n junction. All right, so let's take a look at, this is how a p-n junction looks like actually. So if you have a p-type material, so let's say there are two silicon exist. So I have a p-type material, an n-type material like this. And if I have like separate p-type material, separate n-type material, and I put it together, you see there is a boundary that is happening between them. It's a p-type and n-type. P for p-type. Some will refer as positive, but in fact it's positive by one means only. We will talk about it, then you can simply say, then you will realize that, okay, it's not positive, right? But that's one way to remember positive and negative, but they're not really positive and negative, right? So we say p-type semiconductor and n-type semiconductor. So when you put it together, you see there is a junction that is happening in between them. That junction is the boundary that forms between the p-type and n-type. That is known as the p-n junction. So something will happen at that junction that will make all these devices to behave what they're supposed to behave as. So that's a very important behavior that will happen on the p-n junction. So separately, we can't use it. For example, can I use that p-type only to do something? The answer is no. Can I use the n-type only to do something? No. Any material that you can think of running in terms of the electronic side, it's a combination of p-type and n-type. So they must be placed together in order to achieve some useful task. Whatever that is, it could be diode, it could be transistor. In fact, this one right here is a diode. p-n junction itself is a diode. So when you have a p-n junction, but there is only one junction here, correct? That's a diode. But if I add another junction, that would be transistor. So for example, if I go here, and if I have another material, again this is an another material of n-type. Now how many junctions I have? How many boundaries I am forming? I'm only forming. So that's one boundary right there, and another one is, this is a basis of transistor. It's a transistor known as an NPN transistor by the name of the semiconductor material, right? But there are two junctions in here. This is a very basic form of transistor known as a BJT. But nowadays you have high efficient transistors. So if you go to like Intel or Texas Instruments or any IC or chip manufacturing industries, you will see complex structures. They're not going to look as simple as two junctions. They're going to have like 3, 4, or 10 junctions between p-type and n-type material to make them more efficient. And the size of transistors are, you're right now looking at like 14 nanometer scale That's the size of a transistor, one transistor. So what is nano? Nano is how much? -9. So that's exactly right. So you can think about the size of each one of these devices nowadays. Now the latest one is now 7 nanometers. That's the latest technology right now happening. So it may last for 3 to 4 years. So after that, it will go down in size. That gives us the more computing power. So efficiencies, and there are a lot to it. But this course introduces you to what a transistor is, what can we do, and there are infinite variety of transistors, but all behaves with the same specific pattern. Of similar type, not necessarily be NNPN, but more complex structures. Yeah, if it's only one junction, it's considered as there is only one junction, which is happening between P and N, so does the name PN junction. So if you add another junction, now you have two junctions, then it's going to be transistors. Anything two or more is referred as transistors. No. Yeah, you can have an other way around, but you cannot have a junction with directly two of the same exact type of N-type materials. You may have a different materials for N-type, then you might have that junction. But if you have like two exactly same materials forming one junction, there is no purpose for it. Because if you have, for example, if I have an N-type here, I'm also going to have another N-type here, right? Instead, I can have a one big N-type, right? So forming a junction between two of the same exact materials will not serve for any purpose. So you will see later on, forming a PN junction, what will happen or what's supposed to happen, which will not happen when you have a junction between two of the same materials, right? So it's not useful. Of course, you can form a junction, but it doesn't serve for any purpose, right? So first of all, we will start with the atomic structure, probably from physics or chemistry. You might remember or no at all? Something called as an atomic structure. So atomic structure, what it shows us is the basic behavior of what is known as an atom. So what is an atom? So for example, if you consider copper as a material, so the atomic symbol for copper is a Cu, right? Or for example, if you take hydrogen, right? So in their basic structure, if you take any material for that matter, whether it's a copper, hydrogen, most widely used material in the electronics for diodes, transistors is a silicon. Si, it's symbol for it. So any material that you can consider, the heart of the material is known as an atom. So an atom is nothing but a tiniest particle that you can find within the every given material. For example, if we can say silicon atoms, hydrogen atoms, copper atoms. So if you break an atom to the tiniest pieces, like the heart of every material, and there are a bunch of atoms that are available. So atoms are the internal structure. For example, if you take a solid, right, versus a liquid, all these materials are even gas, right? The state of the materials, if you think about each one of these, there are something known as molecules. Molecules are nothing but a group of atoms, right? That makes the solid material stronger. Because the molecules within that structure of the material are tightly bonded to one atom to the another atom. So if they are tightly bonded, then you will form a solid. If it is loosely bonded, it's a liquid. If they are separated from one another altogether, that's the gas. That's the gaseous state material. Right? They can move freely, basically, anywhere within their structure. But if they are a little bit tightly bonded, then it's a liquid. If that bonding is a very tight where they cannot move, basically one molecule is holding the other molecule very tightly. So you will form a state of the material known as a solid. But behind those molecules, group of atoms are referred as molecules. So that's why an atom is said to be the smallest particle of an element. But if we observe the behavior of an atom, for example, if you have a silicon atom, and if we know how a silicon atom behaves, then we know that how does the silicon material behaves altogether, because atoms will make up the material. It's the same as, for example, if you go for a blood test. Do they need to test for your 1 liter of blood? Right? No, right? You wouldn't be there, right? So all you need is a few drops of blood, right? So similarly, if you test some physical properties of an atom, one atom, whether it's a silicon or a copper or hydrogen, whatever that material is, then we already know the property of the entire structure of that material, because that material is made up of various atoms, right? But what is an atom consists of? So there are various behaviors for an atom is. So what you can see here is Bohr's atomic model. Bohr is a scientist who invented that this is how the structure of an atom looks like. So as you can see, there are various parts in an atom. The negatively charged, when you see a negatively charged, that behaves towards the electron of that atom. Positively charges are known as protons, and there are some neutral charge associated with it. So the neutral charge is referred as an neutron. All right, so neutron is the neutral charge. This is referred as a Bohr's model. So Bohr is a scientist, and this is one way of expressing an atom. But you can look at that electrons are not inside the atom. According to this picture, it's showing that electrons are revolving around something, correct? What they are revolving around is known as the nucleus of the atom. So what you see, this center position right here, this is the nucleus of that particular atom. Whereas electrons are revolving around the nucleus. This model is very similar to like our planetary model, where sun is being the center of all the orbits, whereas all the planets are revolving around the sun. So the planets are like the electrons. So electrons will revolve around what is known as a nucleus of the atom. Right? But what nucleus consists of? Nucleus consists of protons and neutrons. These two are part of the nucleus. That being said, nucleus is a positively charged, whereas electrons, which were revolving around the nucleus, will having a negative charge. So that's what an atom consists of. So if you take a material, you're going to have billions of atoms in there. So If one silicon atom looks like this, all the silicon atoms will look like this, right? So that's how an atomic structure will looks like. Again, here I think there are 1, 2, 3, 4, 5, 6 electrons are here, right? So you can count the number of electrons in here are 6. So does the number of protons, correct? So this type of structure is said to be neutral. So when we say an atom is neutral, what we meant is there are same number of electrons are here, same number of protons are also available. If they are exactly equal, you have positive charge and negative charge which are exactly equal, that cancels out to each other. So the net charge is 0. That's why an atom is said to be neutral in its original state if the number of electrons are equal to the number of protons. So by behavior, most of the atoms are neutral. And there are some atoms are available with different types of, for example, 6 electrons, and I'm going to have only 5 protons. Those are known as an isotopes. We're not going to get too much into the chemistry side of it, but for now, all you need to know is if an atom consists of equal number of electrons and protons, then what is the net charge? The net charge is 0. This is a very important statement to remember, which we will further focus in our discussion on what are semiconductors, right? For example, this atom is actually carbon. You guys know the material carbon? You guys use pencils, right? So carbon, this is atomic structure of a carbon. So carbon has 6 electrons and 6 protons in it, right? Which is not a semiconductor. Carbon is a conductor. You can apply the voltage to your pencil actually, and it will pass electric current. And if you put very high voltage, and it will eventually break. Right? I think you'll see some fire as well because of the wood around it. So, but carbon is a conductor. So this structure is for carbon. So according to the Bohr model, nucleus is the central position of the atom. It's composed of protons and neutrons. And because it consists of the neutrons, neutrons have the no net charge. That's why the most of the atomic weight or the weight of the atom will be within the nucleus. But electrons are very important part of an atom in their behavior, but they will be revolving around the nucleus in definite orbits, meaning that you can see that there are 2 electrons that are close to the nucleus, right? And there are some of them that are a little bit far away from the nucleus. So that's also an important observation to know. The behavior of the electrons closer to the nucleus will be slightly different from the behavior of the electrons as they move away from the nucleus. Because remember that nucleus is a positively charged, right? It's a heavily positively charged location within the atom, whereas the electrons on the other side are around the nucleus. So electrons determines, so that's why whenever we are saying, for example, a conductor or insulator or semiconductor, who's responsible for making the material? So how can I say copper is a conductor, right? Who's responsible to make these is the electrons itself. Because of the position of electrons, materials can be categorized as conductors or semiconductors or insulators. We'll see a little bit more in detail later on. So those are the ones that are responsible for any chemical reactions, sharing or exchanging the electrons with the neighboring atoms. So all the elements are arranged. Probably you might remember this one at some point. Yes. It's known as a periodic table. All the known materials will be categorized in this table. For example, remember I said copper is 6 previously in the copper atomic structure. You see this carbon is 6. It is from the periodic table. So it meant there are 6 electrons, 6 protons are available. For example, if I take silicon, silicon has 14. That's not going to change. That means it does have 14 electrons and 14 protons. Again, the net charge is 0. They cancels out to each other. Hydrogen is right here, which has only 1 electron, 1 proton. Right? So there are various types of materials. Oxygen is right here, 8. Right? Copper is 29 right here, 29 electrons and 29 protons. Sodium is 11, right? But we're not going to, yeah, they all have a net charge of 0 across it because they have equal number of electrons and equal number of protons. Again, the heart of semiconductors is what happens if you have an imbalance. Let's say, for example, if I take away 1 electron, what will happen to the material? Right? So then it would be either positively charged or negatively charged depending upon what I'm taking away. Right? Am I taking away the electron or am I taking away the proton? What will happen if I do that? So all these are arranged in the periodic table according to their atomic number. So those numbers you are actually seeing known as atomic numbers. So atomic number is the number of protons in the nucleus with the same number of electrons in an electrically balanced atom. So we can also say it's a balanced condition is also meant for the atom is neutral. You may change an actual element, but if you have like 2 to 3 atoms tightly bonded together, if you take away 1, then there is going to be some sharing happens between the atoms. Then you may not alter the behavior of the atom, but the properties of the structure will changes. Yeah. They moves. So we will remember the N-type and P-type material. That's where that discussion comes in. What happens if you take away an electron, right? It appears to be that proton is actually moving. So we'll give it a discussion at that point. So when you say balanced atom where you have an equal number of electrons and protons, that's where we say the charge is 0 or neutral. Right? So far down the line in our discussion, we always assume that it's a neutral charge by default in our discussion. So this is actually given by the Bohr's model. That's why it's known as the Bohr's atomic model. So of course, the good thing about this periodic table is you don't need to remember. So the only thing for semiconductors matters is the silicon. So it's good to note that silicon has an atomic number of 14, which is a semiconductor, as opposed to copper is a good conductor for electric current, but it has an atomic number of 29. Right? In fact, germanium, right below silicon, there is a germanium. It has an atomic number of 32. That is also a semiconductor. In fact, the first semiconductor-based devices are from germanium, not from silicon. Germanium. Of course, we didn't invent the material Jamaica yet. Maybe you can go to Jamaica and find out what that material is. But so far, I don't think that we know that material. So let's take a look at in detail. So the graph shows here is the structure of silicon as an atom. So you should be able to see there are 14 electrons. So if you count it, actually you're going to end up with there are a total of 14 in there, right? So remember that the nucleus itself is positively charged, because if this is a silicon atom, there are a total of 14 is the atomic number. So there are 14 protons inside the nucleus. So all those accumulate towards the positive charge. And there are 14 electrons around the nucleus in 3 different orbits, right? So the first orbit, which is closer to the nucleus, consists of 2 electrons, right? The second orbit, you should see it's a total of 8 electrons. And the final orbit should be the remaining 4 electrons. And I can move this all the way up. All right, it's better. So the first statement could be self-explanatory. It's saying that the electrons near the nucleus, which basically talking about, let's say this is our first electron, that's the second electron, closer to the nucleus, have less energy than those in the distance orbits. That being said, if I rephrase this statement, if you get closer, if the electrons are closer to the nucleus, they will have less energy compared to as you move away from the nucleus, the electrons will have stronger or higher energy. So why do you think that is? So why the electrons closer to the nucleus will have less energy than the ones when you're going away from the nucleus? So that's exactly true. So it is close to the positively charged, right? Because remember that opposite charges, you have a force of attraction, correct? So here the nucleus is a positively charged where there is a force of attraction. This nucleus is trying to pull these electrons towards, right? Because you have 14 here positively charged and that's only 1 electron. So the force by the nucleus is trying to pull these electrons. So from the electron perspective, since it is very close in proximity to the heavily positively charged, the electrons itself will have very less energy. But as you move away, the distance between the nucleus versus the electrons are increasing. So the force of attraction will decrease. So the electrons will have the highest energy as you move away from the nucleus as possible. So in this case, I have 4 electrons that are in the outermost orbit, correct? These 4 will have the highest energy, right? Because they are far away from the nucleus. And each orbit has its own energy level, meaning that if we get into detail, we can actually know what the energy of that electron is, each and every electron within their orbits. But that's from the chemistry side of it. We're not going to go too much in detail what's the exact energy voltage of each electron is. But in an atom, orbits are grouped together. In here, if you look at that first orbit right here, it's showing like 2 electrons. But internally, each electron has its own shell, which was quite evident like in the Bohr's atomic model. You can see that right here I have 2 electrons, but they are their own orbit, correct? So instead of drawing like lots and lots of orbits, so it is actually minimized. So we just draw one circle with 2 electrons on it. So it's a more convenient for drawing. Otherwise, you're going to have like 14 times 2, that's 28 circles you're going to have all the way, or 14 circles for that matter. So all these numbers are fixed numbers. So why silicon has a 14 protons and 14 neutrons, that's the atomic structure of silicon. And whenever we talk about silicon, that's where it is as per the atomic structure. But there is a way to find out the maximum number of electrons in each shell by a formula known as 2 times n square. So this 2 times n square will show us the number of electrons in each shell, where n in here is the number of shell. That's how we can even draw the structure of an atom. So like, okay, why it only has 3 orbits, right? So why not it has a 4 orbits, 5 orbits, right? So this formula right here will indicate how many orbits and how many electrons each orbit can accommodate. So for example, here it is showing that the first orbit can accommodate how many? It's 2. But why only 2? Why not 3? So this formula shows us the relation between the number of electrons that can be accommodated in that particular orbit. So if you are talking about the first orbit where n will be 1, so 2 times 1 square. So 1 square is 1, so 2 times 1 is 2. So the first orbit can accommodate maximum of 2 electrons. But silicon has 14, right? So out of 14, 2 will be in the first orbit. So we have remaining 12 to accommodate. So you need to go to the next orbit. For the next orbit, the n value becomes, so the formula is 2 times 2 square. So 2 square is what? 4. 4 times 2 is 8. The shell number. First one, second one, and so on. So for the second one, it's a total of 8. So 8 plus 2, that's 10. So we require 4 more. So the outermost shell. The last one is the third one, right? So if you do 2 times 3 square, how much that would be? 18. So even though it can accommodate 18, all we need is 4 more for silicon. But for example, for copper, you actually go to the 4th shell.
Does it always completely fill up the inner shell before it goes to the next?
Yes. Yep. Hydrogen, for example, hydrogen has an atomic number of only 1. So that means it does have only 1 shell. Right? But that formula indicates that how many orbits we are going to have, and each orbit can accommodate the amount of electrons in there. So how many electrons each orbit can accommodate. So that's the one we can also explain using that particular equation. Yeah. So for a neutral atom, both are going to be equal. So the number of electrons would be equal to the number of protons. So for example, let's take an example. Maybe we want to know, for example, copper. Copper is 32, right? And we are saying that the copper has we're going to end up with 4. Yeah. N represents the number of shell number. Yeah. All right. So let's say we're going to have a copper. So I want you to give it a minute. Actually, I want you to draw the atomic structure of copper with 32 as its atomic number. So I want you to go ahead and actually draw it.